Hello everyone, welcome once again to another lesson. Today we'll talk about the derivatives of e to the x from first principles. That is the derivative of the natural exponential function. We're going to do the original from first principles, stating the theorem first and then proving the theorem. Afterwards, we'll look at other exponential functions. The theorem said let f of x be the natural exponential function, then f prime of x equals e to the x. So let us now show a proof of this theorem using first principles. So using first principles, remember f prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x over h. So f prime of x will be the limit as h approaches 0 of e to the x plus h minus e to the x over h, which is equal to the limit as h approaches 0 of e to the x times e to the h minus e to the x over h. And then that is the limit as h approaches 0 of e to the x times e to the h minus 1 over h. So we can factor the e to the x to the left side, so that becomes the limit as h approaches 0 of e to the h minus 1 over h. Now, in general, we could use the limit as h approaches 0 of e to the h minus 1 over h as being equal to 1 as a fact, but then we are going to show by this theorem that is actually equal to 1 by doing some more math on it. Now consider the limit as h approaches 0 of e to the h minus 1 over h. So we say let e to the h minus 1 be equal to p. So e to the h is equal to p plus 1. And then h now will be equal to the ln of p plus 1 in brackets. So the limit becomes a limit as p approaches 0 of p over ln of p plus 1. And this can be written as a limit as p approaches 0 of 1 over the ln of p plus 1 over p. And so that becomes a limit as p approaches 0 of 1 over 1 over p ln of p plus 1. And so this becomes a limit as p approaches 0 of 1 over ln of p plus 1 r raised to the 1 over p by one of our laws of logarithms. So then we're going to let a letter n be equals to 1 over p. So p is equal to 1 over n. So then now this becomes the limit as n approaches infinity of 1 over ln of 1 over n plus 1 all raised to the n. So this is equal to 1 over the limit as n approaches infinity of ln of 1 over n plus 1 all raised to the n. So this is equal to now 1 over ln of the limit as n approaches infinity of 1 over n plus 1 all raised to the n. But we limit as n approaches infinity of ln of 1 over n plus 1 all raised to the n is a definition of e. So now this becomes equal to 1 over ln e. So then f prime of x is equal to the e to the x times the limit as h approaches 0 of e to the h minus 1 over h. So it's e to the x of 1 over ln e, but ln of e is equal to 1. So that's e to the x times 1 over 1, which is equal to e to the x. All right, so then we have somewhat proved by this theorem that the limit as h approaches 0 of e to the h minus 1 over h, we have satisfied that that is 1. So then we're going to use this as a fact in our next derivatives from first principles of functions with e raised to some power of x, some x. So, example here, let's look at an example. Find the derivative from first principles of this function, f of x is equal to e to the 2x. Okay, so that's our example. Let's pull that back. All right, so that's our example. Find the derivative from first principles of f of x is equal to e to the 2x. So we start with f of x being equal to e to the 2x. So f of x plus h is equal to e raised to the 2, bracket x plus h. Now that our formula f prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x over h. That's equal to the limit as h approaches 0 of e to the 2 bracket x plus h minus e to the 2x all over h. That's equal to the limit as h approaches 0 of e to the 2x plus 2h minus e to the 2x all over h. That's going to be equal to the limit as h approaches 0 of e to the 2x times e to the 2h minus e to the 2x all over h. So that's equal to the limit as h approaches 0 of e to the 2x. You factor that out of the expressions in the numerator. You will have in brackets e to the 2h minus 1 all over h. But we want the denominator of this to be 2h because we have a 2e to the 2h at the top. And so we want the same argument to be in both. The e to the 2h at the top must have a 2h at the bottom for us to let that be equal to 1 by the fact that we're using. So then we can multiply by 2 over 2, so we can get a 2h at the bottom. So that's a limit as h approaches 0. E to the 2x brackets e to the 2h minus 1 times 2 over h times 2. So that's going to be a limit of 2e to the 2x times e, 2h minus 1 over 2h. So now we have a 2h at the bottom. And separating them, we have that being equal to e to the 2x times the limit as h approaches 0 of e to the 2h minus 1 all over 2h. So now that part there is equal to 1, right? The limit as h approaches 0 of e to the 2h, e to the 2h minus 1 over 2h. This thing here is going to be equal to 1. It's going to be equal to 1. So then that's going to leave you with just 2e raised to the 2x times 1 equals 2 e raised to the 2x. So f prime of x is equal to 2 e raised to the 2x. All right, let's look at another example. Let's look at another example. All right, a little bit more complicated. Find the derivative from first principles of f of x is equal to e raised to the x squared plus 2. We're using the formula f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. The f of x plus h here will be e raised to the x plus h squared plus 2. That's going to be equal to, if you expand that, e to the x squared plus 2hx plus h squared x plus 2. So then the f prime of x, if we substitute those into your f prime of x formula, it's going to be equal to the limit as h approaches 0 of e to the x squared plus 2 plus 2hx plus h squared minus e to the x squared plus 2 all over h. So we can separate the e to the x squared plus 2 plus 2hx plus h squared in the numerator. That's the e to the x squared plus 2 times e raised to the 2hx plus h squared. So that's going to be the limit as h approaches 0 of e to the x squared plus 2 times e to the 2hx plus h squared minus e to the x squared plus 2. So we can end up factoring out that e to the x squared plus 2 in the numerator. So it becomes limit as h approaches 0, e to the x squared plus 2, brackets, e to the hx plus h squared minus 1, close brackets, over h. Again, we want to have the same denominator as the power raised to the e in the brackets in the numerator. So we want to have hx plus h squared in the denominator as well. But that would be after you factored out a h, all you would need to do is multiply by 2x plus h over 2x plus h, because you have a h in the denominator as well. That's going to be equal to the limit as h approaches 0 of e to the x squared plus 2 bracket e to the h times 2x plus h in brackets minus 1, close brackets, all over h. And all this multiplied by 2x plus h times 2x plus h. And so now this is going to be equal to the limit as h approaches 0, e to the x squared plus 2 times 2x plus h, close brackets, times e to the h bracket 2x plus h minus 1, close brackets, all over 2x plus h. So now we have a situation, we have e to the h times brackets 2x plus h minus 1, and then over the 2x plus h in the bottom. So then, but that would be, that will also be times h. It also be times h. All right, so don't worry. Now we have the same thing as the exponent, because h times 2x plus h will be h bracket 2x plus h. And so the limit as h approaches 0 of e raised to the h bracket 2x plus h minus 1 over h times 2x plus h, that will go to be equal to 1. And then we have e to the x squared plus 2. H still approaches 0, so we're going to substitute a 0 for h there. We'll have the 2x plus h at that point. So that's going to be equal to 2x times e raised to the x squared plus 2. So that's going to be f prime of x. F prime of x here will be 2x times e to the x squared plus 2. And so that's how you do it from first principles. Thanks very much for watching.